sequencing, these styles have identical tumor. So based on the DNA sequence or the fingerprint, the judge cannot say a particular twin brother is a twin. So they have to let the ghost to go. You don't want to put the wrong person in the prison. Okay. And so there's also another case, which is this lady. He was dating the two identical brothers. Then she got pregnant. Okay, so this is a real case. Okay, so then the judge have to say, well, who is going to pay the child support, right? Who is the father? Based on the DNA, you cannot tell. Okay, so but judge, well, you both pay eventually. Okay, which is probably okay instead of putting one person into the prison. Okay. So then the question is, if for the identical twin, you cannot just use a simple like somatic DNA to identify the suspect. So what are you gonna do? Maybe the lymphocyte, each person has a different arrangement. So theoretically you can do that, but technically because of lymphocyte usually, even now the quincy there's a blood left, the lymphocytes, the number is very low compared to the red blood cells. Okay, so then there's a very trace amount of DNA. Technically, it's very difficult. Yeah. So then based on this genomic equivalence, the the cell differentiation does not rely on the change in the DNA sequencing of the corresponding genes. Okay, so this is a general rule, but we already know the exception for the lymphocyte. So which means there's some kind of a way to preferentially activate some genes. Okay? So this is called a differential gene expression. Okay, so based on this, we can elaborate on this general principle. Is basically each cell nucleus contains the completed genome established in the fertilized egg. Okay, so in molecular terms, DNA for all the differential cells are identical. Okay, except the the lymphocyte. Okay, general rules. Okay. This is the genomic equivalence. They don't use the gene in differential cells and neither destroyed nor mutated. They are there. Okay? So they have the ability to be expressed and to make a protein. That's why you have the trans differentiation. Okay, we talk about the exon pancreatic cells can be trans-differentiated into the beta cells because they still have the same set of the genes there. We're also talking about the supporting cells in the inner ear can be trans-differentiated into the supporting the health cell because they have the same set of gene there. Okay? And this is also the reason why you can do the iPSC. You can find you can do the cloning, the father cloning, the sheep cloning, and from the somatic cells, which is the permanent differentiation. Okay, so another thing is that only small percentage of the genome is expressed in each cell. Okay, so and a portion of the RNA synthesized each other in each cells is specific for that cell type. So, and then you can ask, how different are the two cell types, right? So one thing is that many processes are common to all the cells, like we talked about in the first lecture, like phosphorylation, G-protein stuff. Okay, those are the housekeeping genes. Okay, they are very basic, fundamental for the cell function. But some proteins are very abundant in specialized cells, for instance, in like hemoglobin in red blood cells, right? And typical human cells express about up to 60% of these 25 genes, and the expression level almost the expression level almost every active gene varies from one cell to another cell. Okay. And also very importantly is that this gene expression doesn't necessarily reflect in the protein expression. Okay? This is one thing you have to remember. Okay? People usually, if they don't have a way to look at the protein expression, they will just compare the gene expression by look at the messenger RNA. But messenger RNA doesn't reflect accurately reflect final protein. Okay, so it could be like two cell types. They have the same level of messenger RNA for a particular gene. That doesn't mean they have the same protein expression level. Okay, and so this is the protein and the expression level have this very loose correlation. For instance, okay, this is what happens. Say, messenger RNA level. Okay, from low to high. This is a protein level, okay? And so if you look at the many cells, so you would expect something like this, okay? Have this very nice correlation instead of this. Okay, many dots. Instead of a stream, it's a river. So what does mean? If you talk about same messenger RNA level here, the protein level could be varied very much. Okay, but statistically, they have this relationship. Okay, but most of the time you don't do statistics. You don't do like population. You only look at two cells. So this is something you have to keep in mind. Okay, so it's a river instead of a line. Right? Okay, so this is kind of an ancient way. Nobody using this anymore, I think. Okay. I don't work on this, but I don't see anybody using this. But this is still in the textbook because it's a straightforward way to visualize the difference in the messenger expression in different cells. Nowadays, people just use the sequencing. you do the transcription of the single cells. It's easy, cheap, okay, pretty cheap. So nobody is using this kind of techniques anymore. Okay, but this is you can visualize that. Okay, so basically, you can do like about 2,000 selected genes from the top to the bottom. There's a small division there, small chamber, a small whatever we call, okay? Very tiny there, okay? And then you can do about 142 different cell lines in this way, okay? And classified based on the tissue, okay? Prostate, you have many different cell types there. Lung, you have many cell types, okay? Brain, you have many different neurons and glial cells and so on. Okay, leukemia, you have many different leukemia, and the renal, stomach, and so on. Okay, and so basically you can see, okay, some of the genes, okay, I forgot which one is which, but let's say the red one is the upregulated, the green one is downregulated, the black one is compared to the control, it's the same. So you can see in the prostate, this bunch of the genes is overexpressed, but in the leukemia and the other tissues, they are kind of not upregulated. Okay? And this is non-regulated, but you see here this tissue are operating. Okay, so this will give you a kind of rough idea how different is this, in different cell types, this gene expression. Okay, very different. Okay. And then you want to look at the protein, right? So protein, one way. Again, nowadays people just they still use 2D gels for their mass spec, okay? But you can also use mass spec. Now we just let's say we can put one cell type. We just collect the proteins, we do the mass spec, and we will see all the proteins there. Okay? And also you can quantify how much is expressed. Okay? But this is again, if you want to visualize that using a very simple, straightforward way to look at the difference in the protein expression of two tissues. This is how you do it. You use a 2D gel. Have anybody done 2D gel? 1D gel? You done 1D gel? SDS page? Have you done SDS page? Yes. Okay. So 2D gel is just. Have anybody done 2D gel? No. Okay. So basically 2D gel you do 1D based on the proteins as electric point. Okay. So it's a tubing gel. Okay, you run a tubing gel like this. Okay. So this is the electric field plus minus. Okay, so you put this is a gel. It's a grading gel. Okay, the pH is maybe 9 to I don't know, 9 to 10 or to this is a 7. This is a 4. Okay, you can make this gel like this. Then you put in your protein sample here. Then you apply the electric field. Okay, some protein, because the protein, based on the acid residues, okay, charged residues, and they have a certain electrical point, right? So isoelectrical point means when they reach a certain pH, the positive charge and negative charge is the same. If they don't carry charge, the protein reach to certain pH, they will stop here because the driving force is the charge. When they reach to a certain pH, the histone can be the charge can be varied based on the pH, right? So eventually they will stop here. Okay, another protein will stop here based on the isoelectric point, right? Okay, then you put this, do a slab SDS page. This is the typical SDS page, right? Typical SDS page is like this. So you have many sample well, right? So you have a sample well, you put a sample here, you do a SDS minus plus, right? Okay, so you do this, right? And the protein around down from something like that. So now you don't use the one sample. You just use one. This is lab gel, just one sample, big sample one. So you put this tubular thing, you squeeze out. You put the tubular thing here. So this protein is in this dimension. Okay, the protein is isolated by the isoelectric point. And this is based on this separation is based on what? The typical SDS page. So based on what kind of property of the protein charge. Charge density is proportional to then its movement is proportional to its size. Okay, basically is roughly based on the size. Okay, from large one, okay, to smaller one, right? Okay, so this is how you get this 2-digit. Okay, this is the acidic, basic, okay, pH maybe 4, okay, maybe 10. This is the acid electron point. Doing this. This is based on size, molecular weight. High, low. Okay, now you get a bunch of the proteins. Okay, you will see it. This color is artificially labeled. Okay, you don't see protein like uh, the red or the blue. You can do blue. You use carboxy blue stain. Red you also can do red. Okay, but not here. Okay, this is artificial label. So basically, how you all the red ones are the common in the brain and the human liver. Okay, so you can see these 2 dots. They are the same. These 2 dots, it's right there, and this is kind of there. Okay, these 2, this one is there. Okay, this one maybe right there. Okay, so these 2, you see, they're the same. Okay, so the red ones are the common ones. But you also can see many blue ones. Blue ones are very different. So you can see this a bunch of proteins in the liver right here. High molecular weight, very basic. There's nothing there at all. Okay? So this will give you a rough idea of actually how different the protein expression are in the different tissues. Okay, this table tells you some very abundant protein in a particular cell type. For instance, keratinocyte. This is the skin cell, epidermis. Okay, the major cell types in the epidermis. So they contain this protein. So remember what is this protein? Keratin? We talked about this. Remember? It involves cell adhesion. It's a kind of cytoskeleton, right? So it's an intermediate filament. Okay, so we're gonna talk a little bit more about this. Okay, then red blood cells secrete a lot of, making a lot of hemoglobin. NAND cells, crystallines. B cell immunoglobulin, okay, which also the antibody. T cells, the T cell receptor or cell surface antigens. Melanocyte, melanin, which control the fairness of your skin color. Okay? So pancreatic islet cells, insulin, and Leydig cells, which is in the testes, okay, which is secreted major male hormone, testosterone, and and so on. Okay? So neurons will secrete neurotransmitters, but not other cells. Well, some like health cells will secrete neurotransmitters. So they're kind of considered as some people consider, but I don't consider that. The neuron definition, you need to have the ability to generate action the secret neurotransmitter. And all these the other cell types, okay, they have particular proteins very abundant, which is for their specialized function. All right, so this is basically tell you the different steps involved in the differential gene expression. Okay, starting from the DNA, the first step is you control the transcription. How much is transcribed. Okay, then you make the RNA transcript, and the second step is the processing, RNA processing control. Then you eventually determines in one A cell, B cell, how many messenger RNA of particular gene is made. Okay, these 2 steps. Then you have how many of these copies are transported out, and you want to send it to the ER to generate the protein, right? So before you do that, you also have other degradation control. Okay, then you go into the ER to do the translation. Okay, so how much is translated, and then you generate protein. And even at the protein level, you still have regulation there. So whether you activated this, or inactivated this by some, PTM, including phosphorylation, phosphorylation, and ubiquination, degradation. We already see signal transduction talk, right? So eventually, okay, even you see you say even the protein, like the protein amount, maybe they're the same, but the activity could be different, okay, based on the PTM and stuff like that, right? So then all these factors contribute to the diversity of the cell morphology and shape, morphology and function. All right, so basically that's the first part. Then, as I said, we're gonna jump to the stem cell, okay, first, and then we'll come back to the cell differentiation, cell commitment and stuff like that. Okay. And okay, now let's jump to the stem cell part. Okay. All right. So stem cell. Okay, this is also a very important part of the cell differentiation. And so first, what's the stem cell? Okay. What are the stem cells? Definition. Definition: the stem cells have to meet three criteria. One, not terminated differentiation. Okay? And then they can divide it without limit. This is kind of general, but stem cell can get exhausted as well, which we're going to give you one example. Okay, in principle, they can divide without limit. Okay, and each of the other cells has a choice: remains a stem cell or go to terminal differentiation. Okay, so this is the two scenarios they do this. One is called a divisional asymmetry. Okay, because $2 cells have two options. Okay, it's not the same. That's the asymmetry. Asymmetry. Okay, so divisional asymmetry. So this basically this cell here. Okay, and when they divide, $1 cell is inherently different from the other. Okay, this is maybe some kind of mark on the genes. Okay, and so this cell have this mark and is eventually turning to this is a stem cell, still a stem cell. They can go back to this the beginning of this circle. Okay, and the other cell will go into the terminated differentiation. Okay, so you see this dotted arrow, which means there's any intermediate step involved, not directly. Okay, this is a progenitor cells. Then you go many steps eventually becomes the terminated differentiation. So this is one way to do this asymmetry. The other theory is that, okay, these stem cells, genetically, they are identical, not like this one. This one is sort of, this one is different from that one. Okay. And we're going to talk about this. When we talk about the motor strain. And so here, these two cells are genetically identical, but they, when they divided, they were seen in the different environments, okay? And maybe one is attached to the beta lamina, the other one is not attached to the beta lamina. So when you divide, you see a lot of these cells to see this specialized matrix, beta lamina, okay? So if the one attached to the beta lamina, then remains this stemness, okay? It's still this stem cell. but the other one is off the mesomeria. Okay, and they will go to the third differentiation. Okay, so the dot to the 9 means they're going through some intermediate step. Okay, so this is again, this stem cells. Okay, so this guy is going to determine differentiation. But there's through this process called transient amplifier cells. Okay, they from one cell they will go several intermediate steps. You know, one becomes two, two becomes four, four eventually becomes eight. So this is just an example. We can make more, right? Okay. So this is the reason they do this. Why the nature select this way? Why they theoretically you can do this 8 times, right? So each time we generate this differentiated cells, we can do 8 times to generate 8 somatic cells. Why they're not doing that way? So remember, each time the DNA duplicate, there's a very small chance involved error. Okay, this is the reason why usually the cancers occurs in the most active cells, like epithelial cells. Okay, in the like GI tract, skin, and other monoclonal epithelial cells. Because these monoclonal epithelial cells, their turnover is very high. They have to constantly doing the renew. Okay, so each time you have a very small chance to have some mutation. Sometimes this mutation is harmless, okay? But if you accumulate many, something may go. Okay, maybe one of this, two of this, or more than one of this mutation is detrimental. Okay, right. So to avoid that, so they instead of using the stem cell to let the stem cell divide 8 times, you're using this way to amplify. So the stem cell need to divide once. We avoid the potential error. Okay. So this is an analogy like maybe you have a very famous $1 million painting, right? So you want to make a copy, right? To let people to see it, to appreciate it, whatever. Okay. So instead, you take this. Usually, you keep this in a very safe place. Okay. And but funny story. Actually, I visit this famous art museum in Brazil, São Paulo. So actually, the famous painting you can really like touch it. You can spend it like most of the museum like you have to keep you a few meters away from the painting. Okay, there you can actually see it, touch it. Okay, but of course it's in color by the glass. Okay, which is pretty weird. You can stand in this very famous painting. And touch it. Okay, but anyway, so usually you keep it in a safe place, right? So you want to make a copy, instead you take this famous painting out 8 times to make a copy. Each time you may have occasion to lose it, to maybe spill coffee away, whatever, okay? So you don't want to do that, okay? So instead, you make a real good copy, then use that copy to make more copies, okay? So that will keep your original painting safe. All right, so now this is about this divisional symmetry. How do they get this? This is the theorem, which is called the emotional strain hypothesis. So basically, it says actually in the stem cells, okay, so one DNA strain, okay, and is actually somehow kind of labeled, okay, maybe there's some kind of modification, machination, whatever, okay, so it's labeled. So it's different from the other one. So this will control the standards of the cell. Okay? During the division, all these labeled markers called the emulsions target, okay, target DNA strain will go to one side. Okay? Actually, when they divide, it will sit in the one particular daughter cell instead of the evenly distributed. So that way, so all the cells with this pad DNA strain, this immortal strain, will remains as a stem cell. Okay, this is the one experiment I actually show this asymmetric division. Basically, you use this bromide EU to label this unit synthesis DNA strain. Then you chase it. Okay, then you do the second time division. You find all the newly synthesized DNA will go to the one side. Okay, means there's some kind of, supposedly this dye shows supposed to be evenly distributed into the other cells, but they don't. Okay, so this is the reason why you have this asymmetric divisional asymmetry. Okay, so then this cell, okay, here, okay, you have this, you do, one is remains as stem cell, the other goes to the terminal differentiation. Okay? All right, now let's see why we care about this, right? Why we care about this stem cell thing, okay? Before we do that, we want to know what kind of stem cells we have. Okay, so we have three types of stem cells. One is the ESC, embryonic stem cell. Okay, these cells are from the early stage of the development. Okay, starting from this stage called blastocyst. Okay, this is the very, very early stage of the development. Okay, so you take the inner cell mass cells, and these are the embryonic stem cells. Okay. Then the other extreme is we have adult stem cells. For instance, last time we talked about the muscle cells. There's a sapler cells there. So if the muscle cells is damaged, and then you have this muscle stem cell, which is also called a sapler cells. The satellite cells can regenerate to make a new muscle cells. Okay? And we also have other tissues that have the adult stem cells. And something new is this, is the iPSC, okay, which is basically you can use the differentiated somatic cells, whether it's skin cells, other cells, okay, and you can actually, by some way, you can induce this, okay, to make a stem cell which is similar to the embryonic stem cells. Okay, induce the pluripotent stem cells, iPSC. We're going to talk about the more details. Okay? Now let's look at what kind of adult stem cells we have. Okay, one place you will find the adult stem cells in the epidermis. Okay, this is the anatomy of the epidermis. Okay, so we have 4 layers. Okay, and the bottom, this is called basal cells. Okay, these basal cells can divide and can differentiate it. So the basal cells is sitting on this yellow layer, which is something very familiar with basal lamina. Okay, then this is the connective tissue. Okay, so this is the pelvis. You have collagen, elastin, and have real long stuff. Okay. Blood vessels, of course, for supplying nutrients for the cells. Okay. And so these cells, actually some of these cells are the stem cells. Okay, they can divide. Okay. And then these cells will turn into the something called a prickle cell. The reason called a prickle cells is because they have a lot of this desmos. Okay, and this is also called this desmos is connected with the intermediate filament. This particular intermediate filament is this keratin. Okay, this protein keratin already mentioned. Okay, keratin. Okay, this is one type of intermediate filament. Okay, so then these prickle cells you will turn into granule cells. Granule cells is something that will secrete some semen-like substance. That's here we don't have the pi junction. Okay. Also, even they have pi junction, if you soak the cells in the water, let's say you jump into the swimming pool, what happened? Because the osmotic pressure, your cell will burst. Okay, so your osmotic pressure is about 280 milliosmol. The water in the swimming pool is zero, basically. Okay, so your cell will burst. Okay, if the water directly make a contact with your cell. Okay, so instead, actually you have this granule cells secrete like oil-like stuff that basically waterproof, seal the cells there. Okay, otherwise you're gonna have trouble. So, but the granule cells eventually will die, will turn into these dead cells. Okay, called the keratinized squamous. So this is what actually every day you as I said, you use your skin, okay, particularly your hands, right? So all of your skins, you're under mechanical stress. Think about it. The cells are 70% the water bags. Okay, they easily get damaged by whatever mechanical stress. Okay, even you're wearing clothes, you will kill your skin cells. Okay, so these dead cells keratinized squamous, peeling off all the time. Okay, so if you use a vacuum to vacuum your dust in your house, a lot of this stuff is actually dead skin cells. Okay. So let me give you one example. Okay, when I was a graduate student, I was trying to purify protein. Okay, so I purify this protein. Okay, so every time again we do this SDS gel, right? Do this SDS gel thing. This is a real story. Okay, let me tell you how I can appreciate this. Okay, so I purify this protein. This protein again is a CFPR. Okay, this is what I worked with last time. I'm not working at CFPR anymore. So supposedly, if you purify protein, you will get a pure single band, right? Let's say we have where's the black marker? Okay, anyway. So you put a sample well here, right? This is terrible. Okay, great. Wow, so many markers. All right. Okay, you have a sample well here. You have a sample well here. Let's say you have some sample well here. Okay. Okay. So I run sample like this, right? So supposedly this protein will be 100. I forgot. 180 kD. Okay. All right. So but each time I purify it, I find the protein always there around the 50 kD. And it's not just here, the place I loaded the sample, even place here. Okay? And it's always there, a protein band like this. Okay? Very light, all across this. Okay, staining. So at that time, we don't have the internet yet. That's many, many years ago. I was a graduate student. Okay. So I was, looking to the literature, trying to figure out what this is. Okay. So it takes a lot of time to go to the library to actually read the literature, books, papers. Okay. Eventually, I figure this is the carotene. So how do I get this carotene here? Maybe when I do the experiment, I'm not very careful enough. Sometimes I don't wear gloves. So maybe I touch the solution by carotene from my skin, get into this, right? This is one possibility. Okay, now wear gloves. Okay, very carefully, skim it. Maybe it's the dust, because the dust is full of your skin cells. Okay, get into the solution. Okay, also try some steps to prevent that. It's still there. So where is this coming from? So when the workers in the pharmaceutical company, they make the SDS, make the polyamide, okay? Although usually that's why you need to cover your hair, cover everything, but your face is still exposed, right? So some skin cells get into this. Very trace amount. But this is basically tell you how much keratins are there in the household dust. Okay, in the common place. Okay. So now, because of this incident, I remember the keratin. Okay. All right. So anyway, this is the major household dust. Okay, the skin cell. So this also tell you how constantly the skin cell need to be renewed. Okay, so you have the stem cell to do that, which is it has to be okay. If your skin cells, let's say some kind of mutation make your beta cells not working anymore, then this person will die for sure. Eventually, your skin will wear out. So all the interstitial fluid will leak out. It's like you have a burn, right? You burn the wound, you cannot cover it unless you put a plastic on your skin. Okay, then you have infection. Okay, that's how serious it is. Okay, so another thing I mentioned is the epithelial cells. Okay, so this is again is the gut. Okay, you see probably small intestine or part of the stomach. You have the villus here. Okay, villus. Okay, so villus on the top of the villus, epithelial cells. You also have this lymphoid called crypt, gastric pit. Okay, that's another name. And so this epithelial cell, this is a monoid epithelial cell. Think about it in your stomach. What's going on there? You're eating all this stuff. They have mechanical stress. Okay, making the association worse. You also have what? Chemical stress. What kind of chemical stress you have there? In the stomach? pH, gastric acid, pH 2, 3. So although you have some kind of mechanism to protect it, okay, the mucus, okay, there's some kind of mucin protein, make it like very viscous on the top of the cells. But eventually, this friction, this acid, could damage your cells. Okay, you think about what's going on in your stomach. Okay, so you're eating, drinking, all the stuff. Okay, and this little tiny water bag sacs, okay, will eventually damage. Okay, so this also need to be constantly renewed and stuff. Okay, and so this coming from the stem cells in the bottom of the pea. Okay, this okay, these are the stem cells. Okay, so these stem cells were on the top. They will make this transient amplified cells. Okay, eventually we're coming to the differentiated cells, which including the epithelial cells, like absorptive cells. Okay, this is in the small intestine, is the partial portal cells. Okay, but you also have the epithelial cells. Stomach is the same. Gallbladder cells is the cells secreting mucin. Okay, making mucus for the physical, from the physical chemical barrier. So you also form the interior interplant cells to be secreted by some hormones. Okay. So down there, they also secreted this panic cells. Okay. Divide. This is also involved in response. Okay. So these are the epithelial cells. These are the stem cells for the immune epithelial cells. This has to be constant. Good. Okay. Epidermis and epithelial cells, we all have stem cells. Okay. Muscle cells, we already seen this when we talk about the regeneration of the muscle cell. Okay, so these are muscle is a few muscle multinuclear cells, right? It's fused by multiple myoblasts. Okay, to form this very long fiber. Okay, so you see multiple nuclei there. Okay, so but sitting at the side, okay, this is surrounded by the basal lamina. Remember, okay, sitting this is close to the wall of the basal lamina. It's not shown here. You have this tiny flat cell, satellite cell, okay, which is a stem cell. So when the muscle cells damage, this will turn into the myoblast. You have many of it. This only show one there. You have many. You see right here. This. Okay. So you have many eventually. They will differentiate. They will turn into myoblast. Eventually, form new muscle cells. Okay. But in one disease, what I call muscular dystrophy. Okay. So in these patients, they have a mutation in this protein called dystrophin, okay, which is like scaffold protein, which provides the mechanical strength for the muscle cells. So these patients and because they have this defective dystrophin, their muscle cells is easier to get a damage compared to the ordinary people, like a normal subject. So what does mean? It means their muscle cells need to be more constantly renewed than the normal people. Okay. So let's say for our muscle cells, I don't know exactly numbers. Let's say you want to maybe renew once a day, but for their muscle cells, they need to be renewed maybe 10 times a day. Okay, eventually the stem cells will get exhausted. Although we say the definition of stem cells is divided without limit, but actually they have its own limit. So eventually the cells stop working anymore. So then what happens if you don't have the stem cells? The muscle cells get damaged, right? So eventually you're gonna lose your muscle mass. Okay, starting from this, remember for breathing, you're also using the skeletal muscle. Okay, eventually this patient you cannot breathe it. Okay. So this is the muscular dystrophy. Okay. All right. So for the olfactory epithelial cells, okay. So we also have stem cells here. Okay. So this is the olfactory neurons, and then sandwiched by the supporting cells. But at the bottom part, you have the basal cells, which is the stem cell. Okay, this yellow layer is the basal membrane. So the olfactory sensory cells are actually neurons. They're different from the health cells. Health cells are not a neuron itself. So these cells which have action potential, sending the action potential to the downstream neurons. Okay? And that's why, because we have the stem cells, that's why people don't pay a lot of care to our nose. Okay, you do all kind of crazy stuff to your nose. Look at this video. You see what I did? Okay. But normally you do this to your eyes. You know why? Because your eye, your photoreceptor doesn't have stem cell. You don't do this to your ear because in your ear, the health cells doesn't have the stem cell. If it's damaged, it's damaged forever. But your nose, because you have stem cells, so you can do all the crazy stuff. Okay, if it's damaged, you will be regenerated. Okay. All right. So that's what I just said. Okay, some tissues don't have this have no stem cell. Okay. And in the central nervous system, only very limited area has the ability to regenerate. Okay, most things cannot be regenerated. This is one of the faculty professors to look at the axonal regeneration. Okay, so now let's talk about the ESC, the human embryonic stem cells. Okay. So this is how the ESC look like. Okay, so it's basically epithelial cells. They have incatenating to connect cells together. Okay, so they form high junctions. Okay, these are normally epithelial cells in the early stage. Okay. So you also see that this surrounding cells is like a fibroblast cells there. This is called a feeder cell. Okay, these feeder cells provide some specific factors like cytokines for the growth. You can grow the ESC without the feeder cells as long as you add these cytokines in the culture. Now, of course, it always not expensive. And we just put fibroblast cells make those cytokines. Okay, so that's adherent, right, to the culture dish. Okay, but you can do suspense cells. How do you do the suspense cells? You keep the instead of let the culture media sit there. Okay, you keep stirring the culture. You stir it. So then the cell never get a chance to attach to the surface. Okay, instead they attach to each other. Okay, they form a kind of a sphere, right? So this is in the suspension culture. You keep stirring the culture media when you clean the cells. So this will form this sphere. Okay. So this is called amyloid bodies. Okay. And this is like sort of an early stage of an embryo. Okay. So then with this morphology, this shape, and they gonna differentiate it, okay, to some of the cells will turn into different cell types, like epithelial, cartilage, and bone, neuron cells, and stuff like that. Okay? So this is actually a test to show whether these cells are stem cells. Especially, of course, if it's ESC, they have the standards. But when you do the iPSC, how do you know the iPSCs already have this standards? This is a way to test it, okay, to see if they have the ability to form this different tissues. Okay? And again, this ESC is from the early stage of the embryo blastocyst. So you take the inner mass and see you put it on this culture dish, but you also can do suspension culture to keep stirring the culture medium. They will form this here, embryo body, and then the embryoid body will differentiate into different tissues, cells. This is one is showing that actually this stem cells will make the cardiac myocyte, which has the contraction. Okay. From the ESC to the
stem cell to remarkable potential to develop many different cell types in the body. Survey is the sort of repair system of the body. It can theoretically provide not limited to replenish a cell. When the stem cell revives, each new cell has the potential to either remain a stem cell or become another type of cell or specialized function. This promising area of science leads scientists to investigate the possibility of cell-based therapies to treat disease. In vitro differentiation of embryonic stem cells occurs when the cells are allowed to aggregate in suspension culture in the absence of mouse embryonic fibroblast feeders and leukemia inhibitory factors. These cell aggregates are called embryoid bodies. The hanging drop method is one effective procedure for the differentiation of stem cells into embryoid bodies in vitro.
Today, we will show you a procedure for in vitro differentiation of an embryonic stem cell to the embryonic body using mechanical method. We typically use this method to differentiate embryonic stem cells into cardiomyocytes. This procedure includes the following steps: preparing a single-cell suspension of embryonic stem cells, generating 10-drop cultures, transferring 10-drop cultures to ultra-low attachment plates, and plating embryoid bodies onto jelly coated.
Okay. All right. So there's some basic concept of the stem cells, the potency of the stem cells. The most powerful one is called totipotent. Okay, so basically, the cells has the ability to divide and produce all kinds of the cells, neurons, cardiomyocyte, epithelial cells, muscle cells, whatever, except the even including the actual embryonic tissues like placenta. Okay, so this is a totipotent. Basically, eventually it can turn into all the tissues and even make a full organism. Okay, the totipotent cells, what kind of totipotent cells? So we have spores, okay, so this is for plants, and zygotes. Okay, so but of course the very early stage of embryo is also totipotent. Okay, the last embryo at 8 cell stage. If it's over 8 cell stage, the loses its ability. Okay? And then the next level is the pluripotent. Okay, pluripotency. The cells basically similar to this, except they cannot make the placenta. Okay, so these cells including the ESC and the iPSC. Okay. And this cartoon shows the totipotent cells. Okay, Varuna. This is at a very early stage of the embryo. Right? This is of course also fertilized egg. That's the totipotent. Then you take the inner mass of the blastocyst. That's the ESC we're talking about. So these cells have the pluripotency. Okay, so can make all these cell types except the placenta, and they can turn into different tissues, okay, and also turn into some like cellular cells, which is unipotent. They only can make one cell type, which is the muscle cells. Okay, and then there's a multipotency. Okay, example is the hematopoietic cells we seen before. Okay, so these hematopoietic cells can make all this different blood cells. Okay, but they cannot make any cells like neurons or muscle cells. Right? So different from the polymer. Okay. So this is multipotent cells. Then the other extreme is the unipotent cells. For instance, stem cells in the epidermis, the stem cells in the also the satellite cells. And so if it's something between this, it's called oligopotent. All right, so why we care about the stem cells? Of course, for regeneration. Okay, so as we know, some of the tissues like the hair cells in the inner ear, the photoreceptors, the central nervous system, the axons, and they cannot be regenerated. Okay, so and if you have a problem with this, you need to have a way to hopefully to regenerate. All right, so this is a very hot area. Okay, you will heard a lot of story about stem cell therapy. But remember, at least in the USA, the FDA, okay, Food and Drug Administration, agency administration, I believe, FDA only approved this two. Okay, this is the most updated information. Okay, which is the blood cell formation, basically bone marrow transplant. And the other one is this GDH disease. Okay, it's right here. Okay? Potentially, of course, can treating deafness, we're talking about blindness, because the photoreceptor and hair cells doesn't have the ability to regenerate. Diabetes, beta cells, infertility, wound healing, HIV, heart disease. There's a big scandal, there's a scientist in which university they say, well, there's a stem cells in the heart. Bunch of people work on that for more than 10 years. Eventually, it turns out to be not true. Okay. It's very kind of messy situation. Of course, brain and spinal cord injury. Okay, Professor Liu guys work on the spinal cord regeneration, axon regeneration, and also other central nervous disease. And so maybe in other places the regulations is less strict. Okay. For instance, stem cell therapy, maybe you can get stem therapy in South America, like Mexico, other places, which is prohibited, illegal in USA. Different countries have a different regulation. Some of the drugs can be used in Europe and in Hong Kong, but not allowed in US. Okay. And vice versa. Okay, so I have like super rich friends ask me, oh, can I do this stem cell therapy? Some people recommend this as a one. So all you have to know, only two stem cell therapy approved by at least FDA is this two. Okay, the traditional bone marrow transplant. Okay, and the other. Okay, recently there's also doing the for the eye disease. Okay, these pigment cells, but it's still at the clinical trial. So clinical trial is not equivalent to the FDA approved. FDA approved the clinical trial means they can test on the patients, but they have to wait, see the results. Okay, whether it's effective, whether it's safe, then the FDA can approve them to go to market. It's a different clinical trial. So some people don't know this thing. Especially some rich guys, they have no science background. Yes.
I just heard my mom has some rich friends. They say when they get this stem cell therapy injected, they just feel healthier.
Yeah.
Like,
So
where do they collect these cells? I mean,
where they get the stem cell injection?
How could these stem cells be useful if they're just for someone nobody?
Where they get this stem cells? Where?
I'm not sure about. I don't really know about it.
So in some places like in mainland China, stay in the hospital. That's, I know. Okay, the regulations less strict. Okay. Well, first, how do you know they inject the stem cell just some?
I mean, where do you inject it? Inject it, but you just go anywhere else than into into the cells. If you inject to an area of the skin, then how can we inject and acquire the tissue to grow?
Right. Yeah, there's a lot of issues. But more importantly, all this you feel good. That's why we need a control. We need a placebo experiment. So you know the placebo, right? So and you give patients, they're blinded. So you give two group of patients. One is drug. The other one is just water. You don't tell them. Then you after this, you ask them, how do you feel? So maybe the one with the water, they say, well, yeah, I feel good because that's all they have the treatment. So that's a placebo experiment, the blinded. Sometimes even in a double blind, even the one do experiment, they don't know which one is drug, which one is the water. Why? Because if they know they inject the patient, one maybe this guy is just pretty happy, and the other one pretty serious, safe. So the patient can feel this, right? So you want to double blind. Patients doesn't know. The experiment, the operator for the experiment doesn't. Only the people design the experiment, they know, but they don't contact the patient. This is how you do rigorous test. This is very important, okay? So that's why we get the science training. Because a lot of people, to be honest, even people with the scientific training, with a college degree, they don't know what is exactly the good and rigorous control. Well, that's why you see a lot of nutrient supplements flying all over the place. I have relatives, they are not rich, okay? They are retired, like my uncles and aunties. They're buying all these nutrient supplements. And the stubborn, you cannot convince them. I was like, oh my God. They said what after they have this, they feel good. Maybe they feel good, okay? So that's the placebo effect. So, next time, if your parents are your relatives doing this, you have to tell them, you need a control, you need a statistic to know what's effective, what's not effective. So, yeah, I know there's stem cell therapy. That's why my rich friends, he's super rich, I will tell you, right? So he's asking me, he's like, oh, if I may, like, oh, can we do this? I say, well, don't do it. It's hard to believe, how the rich people were stupidly spend money on something useless. I will tell you. I will challenge you. Okay. But I don't care, of course, right? They have enough money. Okay, so okay, one last thing before we finish the dance is the override. You probably heard a lot, right? So basically, you can use a stem cell to generate an override, okay? So which is artificial kind of organ, or tissue. Could it be brain tissue? Could it be any tissue one kidney, lung, whatever you want. Okay. So reason for this main purpose for this is because you want to use a human ESC to generate this organ. Okay, why? Because you can do all the experiments with the animals. But animals are not human after all. They are different. Okay. Some of the mechanisms are slightly different. Okay. And some are very different. So you want to test on the human tissue. But how do you get a human? You cannot, last time, you cannot test on the human subject unless you reach it to a certain stage. So you want to study to test the human tissue first. But where you get the human tissue? Okay, we have some human cells. But human cells are different from human tissue. Tissue work in different way. Organ tissue work in different way than just cell culture. Yeah. So that's why they want to generate all this. Also, you want to generate disease model. Okay, you make a mutation, mimic some disease model to do this. Okay, this is why this is I think Professor Angela Wu is doing she probably is one of them. Other people I don't know. Because I saw her presentation on brain override. I think
Unknown caller.
And okay, so we stop here. So next Monday, I will try to finish everything, okay, if I can. And we still have basically 1 week to go before the midterm. If you have any questions, please feel free to email me, okay, and ask questions. Okay? Okay, it's open to design. Okay, so all right. Okay, see you next Monday.